And thank you for the introduction. I work at the Atmospheric Chemistry Observations and Modeling Laboratory at NCAR. And this morning, I'm going to show you how to make 6,000 forecast maps in 1 hour. These are my co-authors listed at the bottom of the screen here. This is all in the context of the FireX AQ field campaign, which I'll describe. Then there's a fundamental forecasting problem, which is solved by parallel processing techniques. And I'll show you how I used a dispatcher to launch sub-processes, and then how that applies to other forecast applications. So this is all going to be in Python, as Stefano's talk described. So the FireX AQ field campaign was conducted 2 summers ago out of Boise, Idaho, and Salina, Kansas. Our method here at ACOM was to fly through fire plumes from wildfires and agricultural fires and sample the smoke, both close to the fire and away from the fire, see what kind of chemical processes are going on inside these plumes. The method for modeling was to use WRF-Chem chemical forecasts of air quality to determine where we're going to fly. So the WRF-Chem is an atmospheric model which models air plumes, wind direction, precipitation, rain, things like that, in order to determine where is the best place to go sample. So every morning during the field campaign, there's a flight planning meeting at 10 o'clock. This is an all hands on deck, and the team reviews the forecast. They talk to meteorologists and weather specialists and decide where they're going to fly based on some other constraints that they have. Wildfires typically flare up in the afternoon, and also farmers ignite agricultural fires around midday. So the best time to fly and to sample is in the afternoon, hence the morning meeting at 10 o'clock. I have written a forecast viewer which shows these forecast maps that I've made, and I show it here in 3 panels. This is online. And so on the left panel here, we have a display of a calendar with some hourly controls at the bottom. That is used to step through the images on the right-hand side. The middle panel there shows ozone, which is kind of a dispersed chemical. The one on the right shows carbon monoxide from fires, and this generally is focused as a concentrated point from the ignition point there. So they're kind of different ways these chemicals operate in the air and how they behave. And so these are useful things to show in terms of where you're going to fly. And after the field campaign, we set this up so it would continue running, and it is still running at that URL there. WRF-Chem is our regional atmospheric chemistry model. This runs on the Cheyenne supercomputer at the NCAR Wyoming Supercomputer Center in Cheyenne. The model run begins at 2:17 a.m. Why does it begin at that time? Because there are satellites like the MODIS satellite and the GOES satellite, which detect fires. They send the fires information to the Earth, and we download it and put it into the model, and it's ready at about 2 o'clock. So when we run the WRF-Chem model, we want to incorporate the latest fire emissions. The run usually ends by 5 o'clock in the morning. Here's a typical day for the flight team in Boise. First, alarm clocks go off at about 7 o'clock, and people at 7 o'clock in the morning are reviewing the forecast over breakfast. About 8 o'clock, they go to the airport, and then this begins sort of the 2 hours of huddling in small groups with meteorologists, fire specialists to sort of plan out what's happening today and where they likely should fly. The meeting begins at 10 o'clock in the morning. And so they spend the next 2 hours sort of talking over options and where they're going to fly based on some limited uncertainties, but kind of looking at all these forecasts and planning out their exact flight for that day. Aircraft access begins at noon. So you're filling up dewars with liquid nitrogen and preparing all the instruments. There's a pre-flight meeting. The aircraft doors are closed and usually take off about 3 o'clock in the afternoon. The flight is about 6 hours, so they're going to return at about 9 o'clock at night. Then there's a debrief and maybe dinner at 10 o'clock. So it's a long day. For the instrument team, they usually kind of start at 10 o'clock and say, where are we going to fly today? The flight planning team is sort of on the early side of this day because they're starting work at maybe 6 o'clock in the morning. So there's this overlap in the middle. So you'll see that a little bit later as well. The problem here is that the forecast team has to produce thousands of plots each day. Where all these plots come from? Well, if you multiply 49 hours of forecasts, regions times chemical species times vertical levels. If you do that and multiply there on the upper left-hand side of the screen, you get 5,880 plots. I do this all in Python with matplotlib and cartopy. It takes 5 seconds per plot. So if you do that, multiply 5 seconds times 6,000 equals 8 hours and 10 minutes. If I start at 5 o'clock when the model is finished, it will be done at 1:10 p.m. That's not going to do at all. So at this point, when I came up with these numbers, my co-author and director, Gabi Pfister, remarked that she was concerned about these plots being ready by the time we needed them every morning during the field campaign. I was not panicking because I had some ideas about how we're going to do this, but it's definitely something that you want to address fairly early before the field campaign starts. There's a few other additional considerations which are going to be true of any forecast. Recent forecasts are always going to be more accurate. For a field campaign, the flight plans have to be filed 1 day ahead. So we decide the general region we're going to fly tomorrow. We have to decide that this morning. And for this afternoon's flight, we can make some adjustments sort of specific based on the overall flight plan. And when you have 40 people in a room here, you want to make the very best use of people's time. So first option was to speed up the Python code, use a profiler and find out where I can just kind of bang on the code and improve things. There were things I found such as coastlines. I didn't need the high resolution, and coastlines are pretty expensive in Python and cartopy, so I could reduce the resolution of those. And by some of those methods, I reduced the time by half an hour. So that still won't do. Okay, now we're going to go ahead to the big guns. Parallel processing techniques. How can we squeeze 7 hours of processing time, plotting time into less than 1 hour? So we're going to use techniques that I learned in parallel processing class. These three here: multiprocessing, pipeline processing, and take advantage of atomic operations. So I'll explain what these all are. Multiprocessing is sort of a separate version of multi-threading, but the basic idea is that you start with a main program, launch off a bunch of child processes, and the entire operation is finished when the last of those sub-processes completes. You need a computer which has multiple CPUs in order to carry this out. Pipeline processing is illustrated by this cartoon I've written here. On the left side, the WRF-Chem atmospheric model is generating these netcdf files, and they're coming out the pipeline one at a time and falling on the ground there. And on the right-hand side, we have them stacked up neatly, and we're processing them while output is still coming from the WRF-Chem model. So you start processing when you've received the first intact unit of output. These are hourly files, so that makes sense that these are produced in that order, and we can start on the first one that comes out of the pipe. Atomic operations are a little more complicated. Consider an atom which is indivisible when the operation cannot be interrupted by another thread in the middle of execution. So if something is uninterruptible, we say it is atomic, because in a shared memory situation, we don't want something else to interfere with it. So let's take a look at these A through H here, and which of these operations do you think are indivisible, and which of them can be interrupted by another process coming along? And I'll give you 15 seconds to ponder this. Okay, here are my answers. On a standard digital computer, increment integer is probably a single time step operation, a single tick of the clock. And so that's probably going to be something that is not interruptible. Adding two integers, that's probably also atomic because they fit into the word length, and there is one operation that simply adds them together. Multiplying two floating point numbers, I kind of doubt it. You have to adjust for the scale and the exponent of two floating point numbers. It's getting a little more complicated. Taking the square root of a float, probably not, unless you have some amazing lookup table that it can execute in one operation. Probably that's a multi-step operation. Float matrix to diagonal, this is about the Gaussian elimination and upper triangular and lower triangular. No way, there's a bunch of operations there. Now with F, we're getting to points where it's more applicable to what we're doing here. How about renaming a file? So you want to ask yourself, suppose I type in ls and then return, then I go up arrow, return, bam, 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 back and forth. Am I ever going to catch my friend renaming a file over there, sort of half renamed file? Probably not. So I think that one is atomic for these purposes. Copying a file, maybe a little file, but for a big file, yes, I can catch it halfway copied. How about for transferring a file from Cheyenne to our local computer at ACOM, modeling 1? No way. I can watch it arrive. I can wait for it to arrive. So that is not atomic. WRF-Chem model output is pretty big. We have the files which are about 700 megabytes each. I also have to create a derived file of a few variables here that I cannot get from the model himself. The total output is about 40 gigabytes daily. And at 4 a.m., our sync begins transferring these from our Cheyenne computer to modeling 1. So I'm going to ignore the derive step and just focus on the model output and the plotter. The plotter is firexplot.py. This is uses some of the familiar Python packages, matplotlib, netcdf4, and cartopy. So these are going to do all the heavy lifting. And I'm going to have a dispatcher. Whenever a file arrives, I'm going to assign a plotter to it. Just like whenever somebody arrives on a street corner in Hong Kong or wherever, the dispatcher assigns a taxi to that person, whether it's Lyft or Uber or traditional taxis, somebody's going to get assigned and take that person where they want to go. The dispatcher is going to monitor the arrival of expected files. Dispatcher isn't very big. It's 465 lines of Python code, but it uses the module subprocess collections and operating system to determine what files are out there, and smtplib to send emails. So we're just going to check for file existence here. It's going to spawn the other two scripts asynchronously using this popen command. Now, when computing resources are allocated, what if the worst case happens? What if suddenly there's no pipelining, all these files arrive at once? What would happen if I just launched 49 plotters? Do I need to provide load balancing here? So as we thought of this problem, we've said, well, editors edit, operating systems operate. That's what they do. They're designed to allocate resources. So I was talking this over with Garth, our systems administrator, and he said, let's just try this all at once. We did some estimates and thought it wouldn't be too bad. Let's just launch them all at once, flood the machine on a workday afternoon, leave our doors open, and see what happens. Will anybody come storming into our offices? And before we actually did this, we said, well, what are we expecting? Well, if we had a terrible operating system, it would just freeze or crash. If we had a not very good operating system, it would take hours. There would be no advantage to parallel processing. If we had a perfect operating system, all these threads should complete in 10 minutes. There would be infinite resources, perfect resource sharing, and time slicing. So we're not expecting perfection, but we'd sure like it to be better than 8 hours. Maybe somewhere in between, we have a really good operating system. That's what we'd like to see. So we ran this experiment. Nobody came marching into our offices, and it took 30 minutes. This is the specification for our modeling 1 computer, 20 total cores. The answer was under 30 minutes, so this is pretty good. And I could tell my director, Gabi Pfister, that yes, the forecast will be ready when the airplanes begin to fly. So about a week after she was concerned, she was no longer concerned, and I was of course, feeling much better and pleased that we had such a good result with this approach. So here's what happens minute by minute on the computers every morning during FireXAQ. The first output comes at 2:22, and by 4 o'clock from WRF-Chem, we're up to hour 41. So it's cranking along, but it's not done yet. At 4 o'clock, our sync begins transferring from Cheyenne to modeling 1 every 5 minutes. At 4 o'clock, my dispatcher also begins and starts looking out there for files. The first plot appears at 8 minutes after 4. WRF-Chem and the transfer completes just before 5 o'clock. And then a little bit after 5, the final derived file completes there. So dispatcher finishes at 8 minutes after 5 o'clock in the morning. All tasks are assigned, but remember they run asynchronously, so the final plotter finishes 9 minutes later. So on the right-hand side, I have drawn a yellow arrow there. That hour is where we are most definitely pipelining. We are processing output while the model is still calculating output. File arrival is a tricky thing. This is where I would like it to be atomic, and I had to sort of convert it to an atomic operation. The problem is to find out when has a file fully arrived. We cannot use the size of the file because Rajesh might add some variables or he might take away some variables. He does that fairly often, and I don't want to mess with it. I don't want to have to keep typing in a new file size. So a file arrival is in 3 states. Does not exist. 2, it's in progress, it's still writing, or 3, it's complete. Its size is stabilized over the course of that 2-minute cycle. And then we can begin plotting. So the last note here, this would be easier if file arrival was atomic. So you people listening out there who do models and do things sending information from one to another, consider how it would improve things if you could make file arrival atomic. Because we can be fooled if it stalls for 2 minutes and then kind of goes later. I have never seen that failure case, but if you look at some of the other systems you're familiar with, like downloading things at Windows, there is this thing where you get a partial file, and then as the last step, bink, it's renamed to be the final file that you were looking for. I've seen NCAR CAT do that. Notice that atomic arrival works against pipelining. We don't want the entire 49 hours to be one atom. 1 hour works quite well. The subprocesses are dispatched within Python by calling the, I think it's a subprocess call. I put that in a subroutine spawn in case I needed to change this. But we are, as you can see here from the code, we're calling Python 3 to execute the firexplot.py, and then the other stuff below there is some parameters we're going to send, and then that ampersand greater than redirects all output to a timestamped log file. So if you're going to set up a near real-time forecasting system, you're probably going to want something like this that records all the activity that's going on. In case something goes wrong, you can plow through the log files and see what's happening. Here are the WRF-Chem forecast plots. There's 49 hours, and the total size of the ping files is 1.6 gigabytes, an average size of 272K per plot. So we have taken 40 gigabytes of information and reduced that to 1.6 gigabytes of information in terms of ping files here. So these plots have wind barbs on them and various things. This is a Lambert conformal projection. So I mentioned earlier that you will probably need to do logging here. You're also going to want to send some email to yourself at work, probably at home, to other members of the team. Here's some typical log files, and the emails are similar. So some considerations you might not think of. When the team moved from Boise to Salina, we lost an hour because Salina is east of us and 1 hour difference in the central time zone. So that's going to affect things. You just have to make an adjustment for that. It'll be a bigger effect when the base of operations is in Okinawa. You will probably have a time when the main computer is down for routine maintenance. So add into your script something to backfill. We want a sort of continuous record of plots for this entire period. So you want to think of that when you're writing your software and giving options there. Date timestamps on status emails. I woke up one fine Saturday morning, and after a leisurely breakfast, I went downstairs and looked at my home email. And to my horror, this is what I saw. 10:20 a.m. My dispatcher hasn't begun running until then. Oh no, didn't run until 10:20. What's going on? And then I put things together and said, why is my phone not ringing? It's quiet here, too quiet. Why is the message order begin, complete, progress? Okay, the answer was simple. Thunderbird has its own ideas of when something arrives. So knowing that you should include a date timestamp within the message contents itself, do not depend on the arrival time at whatever you're using to monitor this. So that's an easy thing to do, but it's something you might not think of while you're designing a system like this. We considered a lot of alternatives for where we should run things. And so here's some ideas we came up with, and sort of the drawbacks are shown as the subpoints there with the hyphen in front of them. Plot on Cheyenne and transfer it after that. The fundamental issue here is that there's 40 gigabytes of model output, 1.6 gigabytes of forecast plots, maps, and 5 seconds per plot to generate them. Now you could do it on demand, but then it would take 5 seconds per plot. So that doesn't seem like that much until you multiply it by a 12-hour loop, and suddenly it's a minute. Now that's still not very much, but it would be excruciating in front of 40 people at the airport trying to plan where you're going to fly if just hold on a minute, we got to wait another minute for this new chemical to load here. So that was a consideration. And maybe one of the best ideas here, which is not shown on this slide, was to take the 1.6 gigabytes of total plots, upload them to 10 laptop computers in Boise, and you people have the really fast, snappy viewers here. So you're running everything locally. So that might be a nice way to do that. We didn't think about this until I was making that presentation. So there's various ways to address this problem here. I noted that the flight planning team usually takes breakfast to the airport with them. Why? Because the internet speed is much faster at the airport than at the hotel. What that tells me is that their download speed and their response time really is important. And so I have to work hard to get that in a good shape to run quickly. Now, suppose you are writing a forecast application and there's no planes flying. There's no flight planning team. You still will have the same urgency because the model results, when they are new, they're the most accurate. So there will still be that urgency to get the model results off the supercomputer and onto the internet as quickly as possible. So from the computer to the screen, whatever screen that may be, you will still have this urgency. So to summarize, WRF-Chem Dispatcher was a great success. It just ran. It was just successful. And sometimes the model results were delayed. Well, the dispatcher just sits there waiting and waiting and watching. It times out after 12 hours, but anything before that, it just finds it, picks it up, and starts the plots. So I was really pleased with this. And like it shows here, was prompt and reliable. And I know I've been successful when the people I'm supporting are happy and they're still smiling. Here's Becky Hornbrook filling up the dewar with liquid nitrogen. So the instrument team is happy. And the flight planning team even had some leisure time to shoot hoops in the afternoon while the airplanes were flying out there. So our job, of course, is to support science. And if the scientists are happy, if the flight team is happy, I'm happy. And it was really nice to be able to support these things and have a reliable system that worked and delivered the results when they needed them. And with that, I will conclude and ask if there are any questions.